coming in such big numbers on short notice. I have the extreme pleasure to introduce Robert Stuart Smith, who has been at the IoA several times already. Robert, I read because I couldn't learn the text by heart in 5 minutes, so I'd rather read it and have the precise information instead of producing stuff. Robert Stuart Smith is a founding director of Robert Stuart Smith Design, a co-founding director of the collaborative research practice Computational, and a studio course master in the IoA School Design Research Laboratory in London. Robert studied architecture in the UK, France and Australia, and holds a master's in architecture and urbanism from the Architectural Association School of Architecture's Design Research Laboratory, DRL. He has extensive design practice, experience from the offices of Lab Architecture Studio, that is the people that did Federation Square in Melbourne. So when you go to Australia, this is the project that everybody shows you. The US and the UK before founding RS, Robert Smith Design, and Computational. Specializing in non-linear algorithmic design processes, Robert has also consulted to Cecil Belmont on algorithmic design research and is a well-known design educator through his teaching at a number of high-ranking institutions such as the IoA School in London, MIT in Melbourne, and WU in St. Louis, USA. He's an internationally invited lecturer and critic. And now a few sentences about what you're going to hear. Complex Matter will discuss the expanding role of the architect to engage in the detailed organization of matter for qualitative design efforts. The use of non-linear computational design methodologies that operate through behavioral and self-organizational processes enable designers to address a wide range of practical and discursive issues within the designed architectural expression by challenging the agency of matter, energy, and time. New opportunities arise through embracing generative design opportunities within architectural production. The lecture will include a number of recent architectural projects in addition to work from Robert's studio at the IoA School Design Research Laboratory, which has been exploring the design of qualitative architectural efforts through the rethinking aspects of building life cycles. Welcome.
So after Rainer's introduction, I don't need to introduce the lecture to you. I'm going to start with quite an old video, Godfrey Rizzo's film Clone Scoutsi, that you've probably seen. But it portrays temporal cycles that operate through the flows of people, cars, cities, and the weather. It's an environment constantly in flux. And it's filmed using time-lapse photography, and it just shows things revealed in a different time scale. One where energy and matter become more apparent and perhaps interchangeable. Basically, cities and architecture I see as essentially material orders that operate at numerous physical scales of various durations. So we could consider the built environment as something that's constituted through the flows of material and energy. So a lot of our work, whether it's Computational or Robert Stuart Smith Design, they're kind of interchangeable. A lot of the work investigates a detailed organization of matter, or material organization at a small scale that operates for certain practical reasons, but also for many aesthetic and design ambitions. And these things at a small scale add up to have effects at larger spatial formal scales. For contrast, I'm showing you briefly here a few projects we've done consulting to Rodgkin Architectos on, like let's say, more geometrically focused scripts. So in this case, these are developed by algorithms, but these algorithms could be interchangeable for parametric models. So I'm not actually talking about this stuff today. But maybe to begin with, if we look at this diagram of Christopher Alexander, he's talking here in Notes of the Synthesis of Form about the way that designers engage with numerous design criteria that are in a network relationship. And these have a hierarchy in terms of which ones take priority within design. If you look at people like Frei Otto, you can see them struggling with these ideas through operative models. Like, as in physical models, in this case, the subfield model is negotiating structure with surface tension and form. Or Antoni Gaudi in his catenary models, also dealing with the relationship between structure, form, and space. So these models are operative in the sense that they design through the model. So they find a way where they can generate form, space, while embodying certain criteria, in this case structure. When architects move towards computation, often computation is seen as a way of drafting. We're more interested in qualitative reasons for using computation, such as Stephen Wolfram. Here you look at simple rules of cellular automata, generating unpredictable results, or in this case emergence, a result that has a coherent order at a larger scale. This is in tune with the forefathers of computing. People like Alan Turing's morphogenesis is a demonstration of self-organization. And along with Alan Turing, along with John von Neumann, they are literally the godfathers of the modern-day computer you use. Both advocated for artificial life being possible through computation. So they're not interested in solving simple calculations. They're actually demonstrating that there is something creative that can be undertaken through simple procedural rule sets. We're interested more in complexity theory and chaos, such as this Lorenz attractor, and Edward Lorenz, who talks about the mathematical unpredictability of weather patterns, where they are both calculatable but also creative. So this is an example of, say, a very simple fractal script we developed at one stage. It has interesting complex geometry, it has hierarchy, but it's not the way we tend to work. Like in this case, it's following still a linear set of procedures. This is the way I've just diagrammed out the way code flows in an algorithm here, in different types of algorithms. Parametric models also flow through this way. The way we tend to work is more in ways where a larger organization or some generative effect is created through local or simple rules, such as you can see here. Birds operate that way, such as Craig Reynolds-Boyd's algorithm. Or Eric Bonnevaux and Guy Derlaz have talked about how termites construct mounds through simple local rules as well. So these types of algorithms, I call them, the best way to categorize them is that they are event-driven. And why I think that's really useful for design is that, first of all, it's systemically open. You can keep adding relationships, so you can deal with practical problems as well as design ones. But also, being event-driven, it's easy to use these kind of algorithms creatively because it's a little bit intuitive. You construct events, and each event constructs something that gives rise to an effect or a characteristic in a project. So this can challenge the interrelationships of architectural elements and concepts such as proportion, arguing more for rethinking architectural production as something towards that of a complex organism. So rather than thinking of complexity such as Venturi's idea of contradiction, or as something that's complex to construct, like Gary, we think of complexity more as something on a number of terms, such as Richard Dawkins talking about complex organs such as the eye, being things that are created from heterogeneous sets of parts that perform a useful function. So they're complex because they do something. A car would operate in a similar way in that definition. There's two other ways we look at complexity. Sensitive dependence, which Edward Lorenz talks about, which means, such as this strange attractor on the left, give it a slightly different starting condition and you get a completely different result. Or visual complexity, like on the right. And this one I'm very interested in, obviously, as well. But in this case, if you try to describe that as a geometrical condition with, like radii of arcs, lines, like this would be a hell of a drawing, the snowdrift, the one on the right. A very difficult thing to describe in a traditional architectural drawing. But it's very easy to generate through behavioral algorithms. So it's very easy to create complex, rich detail with very simple rules that avoid you having to describe explicitly what is actually there. So a lot of our work's been developed along those lines. And some of them is purely visual. Like, this is a recent example of a very budget-driven competition in Bulgaria for a rock climbing center, where the idea was just to create a rock climbing terrain that had a sense of volume to it. So rather than feel that it was just applied pattern, that it was almost as if you'd carved out the building from a solid. But it's really just a game of trickery with FC sheet, with the occasional panel being three-dimensional and sometimes being perforated to incorporate glazing behind. So in this case, complexity is just a visual thing, but it's generated through very simple rules and rationalized into something that can be, fabricated in a relatively economical way. Well, per se, it's still a little bit expensive. And yeah, so in this kind of condition, pattern becomes something that is related to surface but came after surface. And then continues, you'll see, for instance, even the facade carries on some of the same patterning. Another project that uses a similar technique, this is a National Art Museum of China. We did in collaboration with Studio Shupe, and this was basically also written through a behavioral algorithm. So in this case, we're talking about giving agency to curves that essentially wrap a series of gallery volumes. And so it's a strange process, but basically the building it had a 3D model, but it was constantly going back from the simulation to 3D model backwards and forwards. But basically, it's defined through a series of autonomous particles in space that move, basically agents. And we are able to control through that a series of connections locally as well, so that we actually define a glazing structure that is intrinsically related in its formation to the form and also to the envelope. And what you see here is a 240-meter long building. The kind of separation of podium and building was something that came from Shupe. What we were trying to do, though, was to give the glazing outline a series of turbulence and variation that kind of broke down that scale a little. Like, this gives you an impression of the scale. You have quite large gallery volumes shrouded in glass tiles. Each of the tiles is the same size and shape, and they're just offset differently. And there's a series of vortexes that define topological manifolds or holes through the geometry to enable light to get down to this podium below. You can see it a little bit more clearly in this 3D print, but basically the whole form, the geometry, is not defined through a model that's been subdivided, but there's actually an organization of glazing that is independently organized on top of that. And so what you see there is something that I would argue has some qualities to it that you don't normally see in architectural projects. Because often, like something that we call articulation is quite often added at the last minute to a project rather than something that forms the project in the first place. And you can see here the relationship between the glazing tiles and the structure. But depending on the quality of light, the structure disappears as well. Another way to explain this also is to look at the landscape tiling of the same project, that depending on what scale you look at it, the order you perceive changes as well. So this also leads into some other ways we actually work through projects using self-organization. It's a similar thing where what we're interested in here is a series of very simple geometries. Basically, it's an agent with a body attached to it, a geometrical body, but the body self-organizing in time relative to the spatial orientation of the agent. And what happens is you actually get a huge difference in time. This is an example from one simulation. But all these are created through elements that are identical. And I think the real interest there is the fact that there's topological variation of the actual body plan, even though the body is not designed to do that. And there's scales of order in, say, a field like this, where you start to see almost fabric-like ripples appearing. So there's an interest in the aesthetic of complexity in the sense that it can bridge multiple scales of effect, and it's not reducible to necessarily the linear gradients you see apparent in other kind of things such as parametric models, which always verge on a band of variation that's predefined. Self-organization also works within more pragmatic criteria that are coupled. So in this case, this is a series of studies for concrete exoskeleton tower, where we're looking at how we can fuse structure and ornament together. And this is a glass sponge, this is a very fragile silica-based ocean living thing that basically it's monolithic in material, but it gains strength and stiffness through the articulation of that material. And we were looking at something similar here, but this concrete exoskeleton, where you have, on one hand, you have a structural system that's based on redundancy. It's not about getting a structure to hit the ground in the most direct route. It's about giving multiple routes for any structural loading to get to the ground. But on the other hand, it's also about ornament, and it's about formal articulation, and it's trying to make these things inseparable. And part of that project was relatively rational to construct, with the exception of that thickened area, to where you can basically form it with void formers from two sides. So it looks more complicated than it was actually aimed to be constructed, unlike this version. This was an airport that we collaborated with Bureau Happel on, where we tried to emphasize the ceiling between arrivals and departures as the priority of the airport, because we kind of felt that most airports, the arriving passengers get neglected, because normally an airport is a big roof structure and you only see that from the top floor. And so in this case, the roof has a thickening to it, and you pass up into the roof from the check-in. So the check-in's on the same level as the arrival. And then you ascend through the belly of the roof into the retail area. It's a little bit more complicated than a normal airport, but the airport planners were happy that it was efficient enough. And it leaves unobstructed views to planes from pretty much anywhere on the arrival and check-in level. And this kind of roof structure, in this case, what we're trying to do is, once again, fuse ornament and structure within one algorithm. So you have a series of strands, like with tens of thousands of agents. Basically, the roof is defined as a fibrous network, and it makes and breaks connections in real time relative to structural loading on the surface. So it's not optimal structure. It's actually a structure that's been predefined by a certain spatial formal condition that we wanted, and then it has to resolve itself structurally within those confines. So that's why it doesn't look like an optimal structure, but all the excess you see there is structural. So what we're trying to do there is, once again, try to not separate ornament from structure in such a way that, if you take away the ornament, you've taken away the structure. Another example of this, but a little bit more smooth perhaps, is a pedestrian bridge in Sao Paulo, where we were trying to convince the client, it looks like this project won't happen now, but we were trying to convince the client to go with carbon fiber, or at least a fiber reinforced plastic, because there have been a lot of case studies done on where you could save a lot of money. So first of all, you decrease the weight, which decreases the amount of concrete needed in pier footings. You decrease the size of cranes needed, transport, and then maintenance costs is a real potential financial saver. So you save a lot of money on maintenance costs compared to steel or concrete bridges. But our real interest in this was to be able to think about how the formal condition, if you were to make it in carbon fiber, formal would become structural rather than just cosmetic. And topology could also become something that enables structure to be more efficient. So basically, how do you get more excessive design potential while at the same time embedding structure? So we start with a tube, and as we gain topological complexity, we gain structural fitness. And as we do that, we also articulate through micro ribbing on the surface. We start to also increase the structural fitness. So the more crazy the geometry, the less material we use. And we start to then take things like stress lines as articulation value. So we could argue that more complexity of geometry led to more material efficiency. That's the bridge. It was a pedestrian bridge to connect a shopping mall with car parking space. And the car park was in a commercial office tower. But yeah, so it's actually quite thin and efficient. Like, it's trying to increase its surface area and volume and depth at various times, but at the same time, there's nothing there that doesn't necessarily work in a sense, either for space or for structure. So this idea of topology led also to a series of investigations, and it's tied to how we can generate topology. So we're looking at people like Lewis Wolpert, who does developmental biology, and basically embryogenesis is a topological process. We're also looking at Stuart, who has these crazy diagrams where he tries to argue that you can almost generate any vertebrate from a base topology of a double torus. And he talks about how you can generate all the articulation of a vertebrate through events that just occur repetitively as a series of procedures. So going back to looking at swarm systems, like agent-based systems are essentially a retraction and repulsion at their most simple, right? So if you have them attract completely, they collapse like a black hole. But if you give them a balance, they start to define something that creates what we call dynamic stability. So here, what you are seeing is a topological condition that remains constant, even though all the positions of the agents are in flux. You see a sphere within a sphere. And this kind of condition starts to suggest that we could use this kind of process for design, but it's very volatile. There's no way here to really do anything meaningful with it, or with kind of instances like this where we can start to define more articulate geometries, but they don't maintain themselves for very long before they disappear. So while the other one was dynamically stable, this one's not. Whereas spring systems, for instance, dynamic relaxation, they do become near equilibrium condition. The sphere you saw was dynamically stable. Those are both two desirable outcomes for design, perhaps, but they're very different in ideology. This is a spring system with an agent-based system, and so what it's doing, it's not trying to create a minimal surface, it's trying to maintain a certain distance from each node to every other node, while at the same time compute the surface area. And we can start to design things like, with this, almost like fabric patterning or tailoring. You can start to construct stranger bodies. Now, in this example here, it's getting stitched together in an almost predetermined way, but at the same time, it's fighting for its position in space in real time. We can also undertake topological modification, where topology is something that arises through the negotiation of a self-organizing system, in this case agents, and where color in this case is describing the surface's knowledge of what it is locally. This surface has no global knowledge, it doesn't know what it's supposed to do, but the local nodes work out whether they're on an edge or whether they, their job is to create a tube or anything like that. So this is about constructing rules. Like when you see the bridge form before, like there's an event-driven rule that was written to say, a few nodes die, a few other nodes reach out and connect somewhere, and then there's a whole other class of nodes that have different roles to play that have to do their job to make that thing happen. So you're talking about a community that has a series of teams with different tasks. That's what that surface is. And for instance, after writing that code, I ran it in a few workshops where you can see these are some examples of something transforming in time. And you can see in this video that's playing, we were trying to basically conceive of a series of events that could happen in time, that one thing would happen in response to the thing before it. So there's a whole, this is just a snippet of a whole lot of videos, but it's trying to think of the generative system as something that's more of an ecology of sorts, where multiple things are negotiating in response to each other. There's no design goal for that. But if you take that, I think there's another version of that here. You can see another one here. So basically, every time you see a color change, there's a rule change happening And everything's just locally organized. Nothing has any global conditioning. But in this case, there's an attempt to try to control some form of geometry through it. And it's just constructing one rule after the other. So using that kind of methodology in a project, we can go completely bottom up. We've done that before, but we can also put in some top-down constraints or some starting conditions. So in this case, this is what I call a design template. It's like the input in which to generate something. And in this case, that's the result. It's a process similar to embryogenesis. The template starts to transform, subdivide, it folds in on itself, it bridges topologically, it does all these strange things, and as it does so, it undergoes a lot of changes. It looks quite deterministic when you see it, but this project was a pain in the ass. Like, this was it took 3,000 simulations. You're going to hate me for saying that, it's not worth it when you see it. But 3,000 simulations, each time writing different code, as well as changing design templates and things. But the thing about it is that all those details you see, like the collarbone-like things on the left, or the ridge on the top, they're intrinsic to the formation of the overall result. They're not something that, we didn't have a model of the geometry and then say, okay, let's add a ridge here, a collarbone here, or whatever. Not that that would be a problem, but I think the interesting thing is it's actually those things that are the telltale signs of how it formed in the first place. Because what happens is when a series of agents or nodes on the surface kind of pinch like that, that's caused a tightening that's caused the whole surface to pull in a very particular way. So it's actually, they're the signs of something local that happened. And, you know, the surface itself, like, in this project, like, the idea was it was a ceramic skin that would then have glazing that would go progressively with transferring across the water, like you can kind of see here. But the main interest in this project, I have to say, it was more an exploration of the research, was to do with the character of the surface in relation to the way it was formed. So it's things like this kind of muscular toning in it, versus the kind of tendon-like qualities. And these things are just things, or in this case the auditorium, which unfortunately looks a bit too Zaha, but the point, I don't show this much, but anyway, the point is the opening there caused a tension that sucked the whole surface in. And so that's why you see all the wrinkles there. It's all part of the way it was generated. It was actually supposed to look a bit like this, but anyway. So in this case you see a formal kind of methodology that's about using bottom-up and top-down, and it's about the character that arises from that. That's the interest, really. I couldn't care less about how it was done. But anyway, it was lacking a bit of materiality, that last example. So after that, we were looking at, for instance, how material order could be part of that problem. So these are quick concepts of basically using the same region in pieces of timber. And this also feeds off what we were doing with the National Art Museum of China. Before we had glass tiles, we were also looking at metal tiles, or metal cladding elements. And trying to challenge this problem, you know, like this kind of, where you have a weird surface and then you have to break it into lots of parts. They're all different. We were thinking more about the fact that you can have interesting difference with parts that are all the same. I ran a fabrication studio in St. Louis where we took that concept. We were looking at structural surfaces by people like Musmeki or, you know, Frato or Candela, and we're critiquing these on the fact that although they perform well structurally, there's something quite reductivist about them as a design. I would argue there's a lack of expression in them. So it's more interested in how you mess with these properties, like how you mix, say, post-tension compression with cable net suspension and drapery. You know, so how do you put a bit of Bernini into Frato in a sense, right? And think about how materiality can be something that is just local, not like as in, let's make something really supple, so it cannot do anything, it's completely useless, and then let's organize it in such a way that it does something useful. So this is the design drawing for this kind of installation experiment. It's the only drawing we need, and it describes how one element is connected to another element. It actually translates into procedures like these ones. And like basically the whole thing is just like the thing in the bottom right, where when it forms a tube it stands up, when it doesn't it collapses, because all the junctions are loose in every direction. So we started by looking at how we could create a ball joint, basically in one direction, and a slotted connection in the other. So this is two axes of cables with plaster models just as a prototype. So we could start testing the same elements doing all kinds of strange things. So here you see they go from surface to strand, they go from tube to surface to strand, and at times they can hold themselves up, other times they become completely like floppy. So to do this kind of thing, the actual base geometry became important. Like what we could define there was what would allow these things to happen or not happen. So there's a series of curvatures, slots that allow for different rotations to occur. This is the final pieces. And you can see here that they interlock, and their curvature means that anytime they slide, they're going to reorientate in angles as well. So they're always shifting in orientation, which is deliberate. And that's the final thing. It's a little bit ugly at certain angles, so I'm curating these photographs. But you can kind of see that, as I said before, this has no structural qualities. That's not the point so much. It's incredibly heavy and it was difficult to build. But it is what it, like the assembly is the creative act. So assembly here becomes generative. Like if you connect them in a slightly different way, you would get a different result. And you can see where it collapses on the other side when you open it up. So this project, this principle was looked into in a slightly different way again in Helsinki Public Library competition, which was for this blank site next to Stephen Hull's Casmo Museum and the Parliament House down the right-hand side. And this time it was kind of an attempt to how to embody these ideas, but actually try to do it in a way that maybe is a little bit finished. And this was dangerous ground. I'm still considering. Actually, I think it's a little bit too minimal for me, but I think it still has some very interesting properties. But anyway, so there's an attempt here at actually working with the context, kind of rotating towards the Parliament House, opening up, aligning to a heritage listed building there and to the city grid, and then opening up towards the park. It's a pretty compact building with all the kind of typical environmental things. I won't go into that. But basically, it opens up towards the park where I'll go into the surface logic of it in a second, but you enter at level 1 from the park or from the ground level on the street behind. And everything is pretty much revolved around this surface, which I'll come back to, which operates as structural support at times, as ceiling at other times, and circulation. And all the elements orientate you, like, towards where you're going. So this surface forms an interior street and a stair up from the park side, and then it starts to wind you up through the building. All the furniture is kind of modular. That's the ceiling above that floor. And you can see where the ceiling comes down at the back is where you see that auditorium on the right-hand side. Now, yeah, this surface, you can also see here where sometimes it's arching, it's becoming post-tension compression, and then other times it's just a suspended ceiling, so it's not doing anything structural. And here you see the modular furniture as well, kind of on the floor. So the thing about this is, on one hand, it looks like a pretty regular project. On the other hand, it has these kind of quirky moments, like you see these warps and ripples and ridges on where you see a little bit of black and the yellow timber. And these are coming from this surface, the surface in the middle. As I said before, the idea here is that the way the material is organized allows it to do different things at different times. So sometimes it's post-tension compression when it comes down as columns, where the two atriums are, and it arches between those as post-tension compression. So there it's self-supporting, it's not supporting the building. But then it's suspended to create a ceiling on the reading level. And the interest in that is that it can be something that guides you as a vectorial space, like it's something that gives you a visual kind of link, but it's also something that provides, let's say, a level of scale or richness to the project beyond the scale of the building itself or the elements such as windows or furniture. But there's a finer grained detail that leads to something else. So in this sense, it's material, but it's also it's a material order or a material scale, but it's doing something at a larger scale within the building. Now this work is still quite, I would say, it's still focused a lot on formal and structural and ornamental considerations. But what I've been running in the DRL studio the last few years is to open this up into a bigger agenda where this, so if you look at this as being, say, practice work, this is student work from the DRL, where we're still focused on materiality and material order at small scales, but we're looking at building life cycle. Thinking about building life cycle not like Autodesk's image here, but as something where we can rethink aspects of building life cycle. We can think about formation as something that's a time-based process. We can also think about temporal cycles within buildings, be they economic, environmental, or social. And we could speculate on different tectonic opportunities that can allow for architectural opportunities, basically. So in this case, we see, like things like Roby House or anything like Frank Lloyd Wright understood with structural steel or reinforced concrete. He could do a cantilever, and then that translates to an architectural effect. So we're looking for what are the architectural effects that you can embody within rethinking certain aspects of life cycle. So seeing production as something you can be creative with, rather than something you take for granted, like this melon, for instance. So we were looking at things like 3D printing, how we could minimize the amount of material needed. So in this case, this is an example of topological structural optimization that was utilized for prefabrication. So where things like a house get interpreted as something that is both ornament and expression as it is structural, and becoming something porous, defined from its actual structural stress lines. And in all these projects, that similar to the practice work, there's a level of detail required, and there's a certain level of computation that's just embraced as part of the problem. Not for its sake, but just for the end results. So in this case, it's a prototype 1.5 meter model made out of 15 elements, where each of those parts is comprised of elements that are often less than 1 millimeter thick. So even as a model, it had to have a certain level of stiffness. And we can control, kind of grains and directionalities, both for structure as well as for expression. We're also looking at things like, as I showed you before, generative assembly, ideas of generative fabrication, even sometimes really simple ideas. Like in this case, this is an experiment with can you make something where you use the last element you cast, say in concrete, as the formwork for the next cast. And if you do it progressively, you can start to generate all kinds of complex curvature. And in this case, the difference between these two is one of overall form, but it's also one of detail. And that detail gives you a little hint of the history of how that was actually made. So it's an idea of embedding within the fabrication process qualities that come from the way it was generated. It's similar in, say, this kind of example in a workshop we did, where this pattern, when you let it go, generates this, just through simple relationships of tension within wire and also tension within lycra just playing off each other. So there's a fight between the two materials, but one that's not equal. And we can speculate on these kinds of things in larger projects, such as this habitable bridge, which considers fabrication and assembly as things that can be kind of really worked through as a design problem. So in this case, it's using fiberglass, where by unwrapping parts of the project, we can integrate everything, handrails, stairs, and then the actual fiber placement also takes on both a practical a structural role and an aesthetic role. So you'll see here it has patterning, it also has segmentation, and these are things that are both aesthetic but also intrinsic to the whole production process of the project. So the project's fabricated in unwrapped fiberglass parts that are then hung. We use digital simulations in the studio in DRL as well as in physical models like this one. The whole project gets unwrapped and it's designed as a series of prefabricated parts that are basically delivered to site unwrapped, and then they're hung on site in a scaffold and cured with resin. And then they're assembled without scaffolding. So each part is designed to hold the next part. And this was worked through with AKT structural engineering as well to the conceptual level. So in theory, we could cantilever, huge chunks of fiberglass by just designing the way one part inserts in the other. So this kind of render becomes part of the project. I would say that kind of render was just as important as this render, in the sense that it's communicating the logic behind the project. Similar things that we've worked through with cutting sheet steel and aluminium and inflating it. I won't go into that too much. But it's both a technique-driven way of generating space and form, as it is a way of rationalizing material. In this case, trying to argue for mass production using just sheet steel delivered to site that was then inflated on site. And that involves, this was a housing project, but it involves thinking at multiple scales. And so even at the level of, here they're describing apartments, but you can't separate their planning from their material articulation from their structure. This also pushes into ideas of generative temporalities, where we work with things like mushroom, mycelia fungi, and for instance, considering relationships between mushroom and rice, and how mycelium fungi can bond with a substrate, such as rice hay, and we can work out logistics for structural support to have concepts such as this. So basically, this concept here, if you imagine that's 1 story high of space, like a canopy, it's basically using an agricultural tube of rice hay, a product that's off the shelf, and developing it into something that can become self-binding and self-supportive with the mycelia fungi. This is an example of how they actually work through the project, where the size of the project is based on the production capabilities of the site, like how much rice hay, how much mushrooms can be done, and how that gets staged in time. So the project, it gets rebuilt every year. It's in a little window of when they decide not to produce rice, and they build it in stages. So as one part of the project is actually growing mushrooms, the other part's getting demolished. These kind of logistics move into things like water control. We have here surfaces that absorb, they have hydrogel and they absorb water, and we can redirect water in time just by controlling the weight of the surface. So as an envelope, for instance, stores water, but then at a certain point it could redirect it. These kind of principles have been worked through with erosion as well. Here, students had to work through their own computational models of erosion to do things that weren't easy to do in off-the-shelf software, such as water tracking on the underside of a surface. I think you probably have had to detail drip grooves in construction class before, but water always runs on a horizontal surface, it sticks to the underside because of surface tension. In this case, we want that, but we just have to work out how to simulate that kind of thing, so that we can do things like this, regroup water over time. So that as a building erodes over 12 months, that when it gets to a certain season, we can change where the water running on the roof of a structure goes at a particular time of year. To do this, we work through scale models. In this case, this is a model that was eroded over 6 months. The students set up a rain machine at school. They ran 24 hours a day for 6 months. And they developed simulations so they can speculate it on things like a public bath building in Sao Paulo. The interest here, I'd say, is that the building is designed to survive 10 years, and one part of the building is designed to be rebuilt every year, so it becomes porous. Other projects have looked at the relationship of water collection and distribution in relation to structure. So here you see an Asian-based system that's working on how to distribute water across the surface so it can be absorbed everywhere evenly within the surface, but at the same time trying to play that out against structural concerns. Like, so the most efficient structural arch would be a steep one with a small span. The best thing for collecting water across the whole surface would be a shallow arch with a wide span. So they're playing off these kind of contradictory scenarios and working out how to embody them within Tectonics that they prototype versions of to design a building proposal that basically collects water over a period of time and redistributes it in different times of the year. And once again, the ornament of the project, you could say, or the visual kind of interest, is related to the practical aspect of the project. And that works at a greater level of detail. Maybe the last thing I'll show you, which is a little bit abstract, is going back to think of these things also through materials. So this is playing out with the surface tension within silicon and wire. And it's something that's just, it's an inflatable thing working at regulating water and air. And it's complete, there's nothing in that was actually, let's say, designed beyond designing the fabrication technique. So it's like gaining levels of sophistication, let's say, in what we can make by actually engaging with the materials as well as with computational processes. So all the like ribbing and fluting in that and the way it distributes fluids is just part of the way it was made. So it's like, in order to create some of these things, we're trying to create the way we make things as well.
If you have questions, Robert will answer them.
I might just summarize it. I guess maybe it was clear, but maybe it wasn't. But the interest really is in how to find ways of expression that are somehow embodied within the way we make things, whether that's digitally or physically. You know, and just how they can add characteristics to a project. It's not so much the practical side, it's just the interest in finding different means of expression. Any questions?